One of a famous instance of gravitational lensing is called Einstein's cross. Again, in the center of this image, we have a galaxy, and the 4 points of light are all images of a single quasar which lies far behind the galaxy. This is another image of the cross. So this is a quasar. There's a large galaxy here, and there's actually several examples of gravitational lensing in here. So there's a set of quasars and a set of galaxies, which you can see here. So these 4 plus another one, which is hidden by the galaxy, are all images of the same one. And then you have 3 copies of a galaxy that lies beyond it. Another effect of gravitational lensing is that not only do you get distinct images, but you can get those images can blur together, and you get what are arcs and rings. So here you have your gravitational lens, which is the red galaxy, and then you have this arc, which is the lensed image of a galaxy or a quasar, which lies beyond that galaxy. In addition, you get, not only can you have things, suns, stars, so the sun, or galaxies, but also clusters of galaxies. This is a very big one of the largest clusters, and it's a little bit hard to see, but you have arcs here, 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 here. There's a whole bunch of arcs. So this massive lens is just distorting everything. A final effect is that those arcs that we just saw can actually expand all the way around your lens, and you get what are called Einstein rings. So what, other than making some really cool pictures, what can we do with gravitational lensing? And it turns out, with gravitational lensing, is a powerful tool for finding objects in space that you wouldn't be able to see directly. Specifically, planets and black holes. As well, it can be used to map the dark matter in our universe. So to find things like black holes and planets, we can't rely on what's called macro lensing, which was what all those other images were of, where you have really big effects. All it is a small effect. So what you get is that, just like a regular lens, if you put a regular lens in front of a light source, that light source will be magnified. So, and that is what is the basics for microlensing. So this here is a graph of a typical microlensing event. So you've got the standard output of whatever your background source that you're using as your reference, whether it be a galaxy, a quasar, another star. And then you have this spike, which is another object passing in front, or passing between the Earth and your distant object, and how its lens is increasing the brightness of that background object. So you can use this to detect, if you're watching over a long period of time, you can use this to detect microlensing events. This is actually a picture of the cross that I mentioned earlier. And so the galaxy in the middle contains stars and it contains planets, and those planets on occasion cause microlensing events. So a planet passed through the path of light that was creating this image, and you can see that it is much brighter. Now, in addition to just seeing as a single object passes in front, planetary systems have the fact that they've got their one large lens and their smaller lens made by the planet. And if you've ever looked in a pool that's on a sunny day, you see really, really bright lines. And they're called caustics, and it's the combination of two lenses can create really distinct spikes. So here you've got your regular path for the star, and then you have this spike where the gravitational well of the planet was in just the right location that it significantly amplified the background. So using these techniques, we can find the location of stars and of planets that would just be impossible to see otherwise. Now, the second application of